I gotta close this. Let's start that. We got things going, things moving, shaking, all the things. PowerPoint being PowerPoint as usual. All right, so we're gonna do some problems, and we'll talk about rotating unbalance. If we don't get to rotating unbalance today, we'll cover it on Tuesday. It'll be fine. But we'll at least talk about what it is today. And it turns out that you don't need to do rotating unbalance for the homework anyway, so nice how that works out. Here's the plan for the rest of the semester, right? Here's the plan. Well, we'll talk about that in a second. I'll talk about the plan first. Here's the plan. Today, we're going to do a couple problems, okay? And talk about rotating unbalance. Tuesday, we will talk about whatever we didn't finish today, plus the case study that I want to do to show you guys how we can apply this in the wild, like to a real problem. All right, so we'll do a case study problem, and then the rest of class, whatever time we have between then and the final 30 minutes of class, is up to you guys. So if you have any questions, anything that you've been studying, any concepts that you want me to go over again, that's a great time to do it. That'll serve as a kind of our exam review, but it is led by you guys, not by me. So you have to tell me either before that class or during class what you would like us to talk about, okay? The last 30 minutes of class on Tuesday is your makeup points, right? Now, it applies to question 19 from the exam, right? So for those of you who didn't read the post in LoudCloud or the one on Discord, doing test moz was an epic failure on my part. I cannot allow you back in to see those results. What I did do though, which will allow me to do, was print a PDF of all of your results individually and then upload them to LoudCloud, which worked. I hope everybody can see them. I hope all that. So go into LoudCloud, check the Exam2 Dropbox. There should be a PDF in there with my comments on it. Right, you guys all have your work. Hopefully, you didn't throw it out. I would highly recommend redoing problem 19 and making sure that you understand how to do it, because it's going to be, your makeup is going to be very similar to problem 19 from the exam. Okay. How does the scoring work? You will be able to make back any points that you lost on problem 19, and I will replace it as long as you did better, right? If you did really well on problem 19 and you don't feel like you want to try to take it again, you don't have to. This is completely voluntary. But if you want to try to max any and all points available to you, you can feel free to do it as well. Once you're done, you'll get 10 minutes, right? I think I said 10 or 15, I forget, it's one or the other. But you'll get some time, since it's one problem, scan it, like take your pictures and submit it. Submit it as a private message. Submit it as a private message to me, right? And we'll go from there, right? And then I'll grade it and I'll update your exam grades accordingly. Right? Pretty straightforward. So let's talk about this. Transmissibility attenuation. Man. Woo! It's a lot. All right. Let's go. Right. So last class, they also had some questions about transmissibility, right? Transmissibility is what? And this is the part where I look confused. Oh, by the way, this picture, yesterday I was in a meeting, my background, and some people asked me if those were my kids. So yeah, they're not my kids. I'm not that old. Okay. Anyway. So what is transmissibility, right? By definition, transmissibility was defined in two different contexts, right? It was defined as the amount of the amplitude of the input, or I'm sorry, the amplitude of the transmitted displacement divided by, right? So if we look back at our notes last time, it was defined as this, right? And this is for displacement, and that's TR. And I apologize for the glare there. You can kind of see it. It is also the amplitude of the transmitted force divided by the input force is also equal to TR. Both of these are the same, right? TR is TR. TR is not different between the two. They will have the same TR. Okay, now that we've said that, but what else is this, right? Well, this is the amplitude of my output to my input, right? The ratio of my output to my input. Well, isn't that just this? The magnitude of G of J omega? And it turns out that's, yes, is exactly what it is, right? The transmissibility is the magnitude of our system. And transmissibility, by definition, tells us how good our system is at handling vibration for a specific frequency, right? And so a high number, a large number, tells us that we are amplifying our vibration, right? Numbers greater than 1 would be amplification of our vibration. Numbers less than 1 would be attenuation, right? So remember, attenuation is just the opposite of amplification. Amplification is the multiplication of our signal by a constant. Attenuation is the division of our signal by a constant. Okay. There's one more thing that I want to try to cover here, because this is something that's come up from a couple of people in office hours, and I think that it's helpful, but we'll find out, right? So I want you guys to remember, everything that we're doing in the frequency domain happens in the S plane. You can't see the top there. That says imaginary. So the real imaginary axis for the S plane, right? So this is the S plane. When we first introduced the idea of the sinusoidal transfer function, right, there was this equation that showed up on the screen that said G of J omega was equal to the magnitude of G of J omega e to the J phi, right? And we said that this is what? This is called the polar form of the equation. Okay, so in the real imaginary axes, we can draw this, right? Imagine that this is some vector that has an angle phi that's associated with it, right? It's got some real component, it's got some imaginary component, right? But this is also equal to this, right? Which means this is where I'm going to use different colors. You'll see why in a second. But we can write each of these. If we wrote it totally in polar, right? We write everything here in polar. I have to do that. We write everything here in polar. So G of J omega e to the J phi is equal to y, magnitude of y of j omega, e to the j. I'm going to call this phi sub n because it's in the numerator. Doesn't matter what the variable actually is, right? It's just they need to be different. And this, where we have phi sub t. Right? Okay? So we have this total thing, and it looks gross, and it's in polar, right? But the one thing that we can take away from this is what? All of the magnitudes, right? This magnitude, well, let me rewrite this equation one more time. Let me rewrite this as y of j omega magnitude divided by the magnitude of u of j omega. And I'm going to use my exponential rules to have e to the j, phi numerator minus phi denominator. Right? Because if I have two things that are raised or that have the same base, right, and I divide them, that's the same as subtracting the exponent. Okay? So I've got this, and this looks gross, right? But this allows us to simplify pretty nicely, right? Because if I can get the magnitude of the top and the bottom, and I divide them, that has to be equal to the magnitude of g of j omega. And anything that's e to that power has to be equal to e to that power, right? So that total phi, the red phi, has to be equal to the numerator minus the denominator, right? The angle of the numerator minus the angle of the denominator. Right, we kind of went over this briefly during one class, but why is this important? Well, I can draw these, right? I can draw this and this both on my plot as well. And so I end up with something where this purple line is y of j omega. It has some angle phi sub n. And this green line has some angle phi sub d, right? And corresponds to u of j omega. Now look what happens, right? You know, it's not perfect. I didn't draw it perfectly, right? But you subtract those two angles, you get the angle that's left by the red one, right? You combine these, divide these magnitudes, you'll get the magnitude of the red line, right? So in a lot of our cases, right, in a lot of the examples that we have been doing, we've been getting a numerator that's just a constant, right? Just has a real portion. And something with a real portion only falls on the real axis, right? And phi is our measure from the real axis in radians. And if we're on the real axis, then phi is 0, right? So that's what we've been getting for our phase for the real portion. Right? If you're given something, I don't know, I'm going to make one up right now. Say we have this transfer function, 1 over s squared plus 5s plus 25. All right, this is our transfer function. Make it into j omega. 1 over 25 minus omega squared, right? Because j omega squared gives me negative omega squared, right? Plus 5 omega j. The imaginary portion is 5 omega. Well, let's just say omega is 1 for right now. I can plot that, right? I can plot that right here. If omega is 1, that's just 5j. 1, 2, 3, 4, 5 in the j. 25 minus 1 is 24. So it's like over here somewhere, right? So my vector would be over here for the bottom. The numerator would just be a line with magnitude 1 on the real axis. Then you're just trying to find the magnitude of the transfer function, which is in the math, right? So you can do all of these graphically if you want, right? Doable. Is it necessary? No. Is it helpful? Debatable. Might help you to conceptualize what's going on. If it doesn't, you always have the equations to fall back on, right? But this is where it comes from. Right? All right. Was that helpful, not helpful, indifferent? A, B, or C? All right, so do you guys have any questions, right? So how does this relate back to transmissibility, right? Well, we already kind of talked about that, right? But transmissibility is just this, right? It's just this magnitude. That's what the transmissibility is. That's all it is. And what is transmissibility telling us, right? Transmissibility is telling us that at a specific frequency, right? Say I have this device and I start shaking it, right? Say I have this device and I start to shake it. And I want to, let's use this, the electromechanical system lab, right? I turn it on. It starts to vibrate at a specific frequency, right? Which is equal to the angular velocity, right? As this is rotating at that constant omega, I get a sinusoidal output, yeah? I've reduced that as it's gone through, right? So I have low transmissibility because I start off with a large displacement, and as it moves from mass to mass, it lessens and lessens. So the transmissibility of this system at omega has to be less than 1. But the opposite is sometimes true. You can have a spike, right? We saw that in our Bode diagrams for second order systems, around the resonant frequency, you will get a peak. And in certain cases, that means you're going to amplify your input. So in the case of a displacement, if you were to put in 1 centimeter, you would get 3 centimeters out, right? If you were if you had a transmissibility of 3. Same thing with force. If you were to put in 1 Newton of force and you have a transmissibility of 3, you're going to get 3 newtons out. Okay. Are these good? Is this bad? It depends on your application, right? There's certain applications where we would want force multiplication. There's certain applications where we want to attenuate our vibration out, right? So it all depends on what we're trying to do. Okay. All right. Again, attenuation is just the opposite of amplification. Right? Attenuation is just the opposite of amplification. Often as mechanical engineers, biomedical engineers, we will want to attenuate vibration because it wreaks havoc on physical systems. If you're into the sensor sides of things, there's a lot of applications where you'd want to amplify vibration, right? So electrical engineers tend to like to be near resonance or near natural frequency because of the ability to amplify that signal. Okay, there's one more thing I want to kind of talk about quickly, right? Since we're talking about transmissibility, and we'll go over it one more time. I'll bring it up. I realize you can't see this. Please hold. Right. When we were talking about transmissibility, we came up with this, what most people feel is a convoluted equation to determine transmissibility. But the reason that we do this is very specific, right? Because we want beta. We want this frequency ratio. And what is beta? What is the frequency ratio? It's the ratio of my input frequency to my natural frequency, right? And if we get this in terms of beta and zeta, it allows us to graph this plot, okay? Where beta is increasing on the x-axis and my transmissibility is given on the y-axis, and each of these curves has varying zeta, right? Has a different damping ratio, right? And what are the things that we want to take away from this curve, right? First of all, beta is equal to √2 is the magic number. Anything higher than that, and we are guaranteed to attenuate our vibration, right? We will have a fractional transmissibility. Anything larger than that, and we are guaranteed to amplify, right, our vibration. We will never be under 1 unless we are to the right of √2, unless we are greater than √2. Okay? How do we get greater than √2? And this is what we need to talk about. This is where the rubber meets the road, so to speak. Right? So how do we get greater than √2? Let's talk about that. To talk about that, I'm going to put that up on the board here. Remember, beta is omega over omega n, which is omega over the square root of k divided by n. Square root of k over n. So if we want to change omega, right, how do we get this number, beta, to be really big? We either jack up omega, right, at a known natural frequency. We either just pump up our input frequency to really high levels, which might not be something that we can do, right? We know that we're operating over a range of frequencies that are set. So how do we change omega n? Well, we'd want to minimize it, right? Because by making the denominator smaller, we increase the size of our overall fraction. How do we minimize omega n? Well, maybe the mass of the system can't be changed, right? Because it already exists physically. So what do we have to do? Well, we have to increase the stiffness, right? So you increase the stiffness, you decrease the stiffness, decrease omega n, increase beta, right? We get beta over √2. Then what's the next step? Two times zeta omega n is equal to b over m. So therefore, zeta is equal to b divided by 2 zeta, well not zeta, sorry, 2m omega n. Oh my gosh. All right. These are set because we already set them. So how do we want to manipulate this, right? How do we want to manipulate this? Well, if we are already greater than √2, we want to decrease zeta, right? Because why? Just look at the plot. After we pass √2, decreasing zeta gives us more, or rather gives us more attenuation, right? Or less transmissibility. We will transmit less vibration. If we are stuck and we can't lower it below √2, we want to maximize our damping ratio. Maximizing our damping ratio will decrease the transmissibility in this to the left of this point. But that trend reverses once we cross √2. Okay? Now, are you going to need to, practically speaking, right? Practically speaking, are you going to need to draw this curve? No. Do you need to understand what the magnitudes mean for different things? Yes. And we'll go over an example later about how we can use transmissibility, right? Because sometimes you'll be given a range of transmissibilities that are okay, right? You'll be told, you know what? This system is fine as long as we don't exceed twice twice the input, right? And so you keep the transmissibility less than 2. But we need to be able to look at a Bode diagram and understand what frequencies we cross that are out of bounds now, because we have too much amplification of our signal, right? Okay. Okay. You guys have any questions about that stuff? Any other questions? No? He's doing all right. Maybe. Okay. Here's the stuff that's due. Some of you have started the homework. Some of you may not have started it. Turn it this way and start your homework today. Okay. If you start your homework today, the added benefit is that there are office hours tomorrow, so you can come in and ask questions. So please start it soon. Like I said, you guys hopefully, that's part of the studying is doing the homework, right? But hopefully you've also started looking at some of the other concepts and things. Next week on Tuesday, we will have a little bit of time for review. So if you have any specific questions, we can go over them then. Exam 3 next week on Thursday, benchmark and presentation, right? So again, if you guys have questions on the benchmark or the presentation, you can ask during office hours, before or after class, right? Whatever is easiest. Okay. Office hours leading up to the exam are Friday, 3 to 5, Monday, 9 to 11. Although I think one of my senior project groups is meeting on Monday, so stay tuned. That might get postponed by a 30-minute window. Yeah. What time are they in? 9 to 11. But I think I have, give me a sec. I'll pull it up. I'll tell you exactly. Monday the 14th. Yeah, it's going to be 9 to 10:30. 9 to 10:30. Okay. Tuesday. Tuesday is going to be 3 to 3:30, and then 4 to 5. I have another presentation I have to be at in that time. Wednesday, 3 to 5, and that brings us up to the exam. Okay. All right. We've got today's class and we've got Tuesday. Okay. Today's class and Tuesday. We already went over the plan. Is everybody cool with the plan? Everybody understand the plan? Okay. All right. So this is what we're going to start with today. We'll go through this one together. All right. So above is a simplified diagram of an optical disk drive system that uses a laser to read data stored on a compact disk, such as a DVD. So you guys, a DVD is kind of like a Blu-ray, guys. Kind of like a Blu-ray, for those of you who don't know. Okay. So I'll tell you, it's not really a story, but I'll talk a little bit about this. So has anybody ever had the experience of going in an RV and bringing a game console or a DVD/Blu-ray player and trying to watch it while driving? Yeah, and normally that's okay for a little while, right? But then you hit like a bump, and your DVD and your Blu-ray disc or your game are no longer usable after that play session because scratches from the laser, right? Typically. But it's okay for a while. Just not great with low frequency inputs, right? Back before MP3 players, back in the day, people had these things called Sony Discman, ran, and it was it's a portable CD player. You guys know what they are. But I had one that was real fancy that had the anti-shock stuff on it, and all the anti-shock stuff is just this. It is a vibration isolation mount. Why? Because you want to be able to run with your CD player without it skipping every step that you take. Or maybe you don't want to run with it, maybe walk lightly. But all right, anyway. What we want to do is we want to create a model of this system. We want to find the vibration frequencies for an impulsive input due to a sudden displacement of the phone. Hold on a second, Dr. B. Pump the brakes. I thought for frequency response, we had to have a sine wave input. What is this impulse business that you're talking about? Just hear me out. We'll get there. And we want to analyze the frequency response by looking at the Bode diagram, right? And we want to do all of this for the pickup head. So this system has a chassis card. So the way that it works, right, similar to a record player, right? You start your record player towards the center, and as we go, it expands outwards, right? DVD, CD player, same deal, except that we do it with laser instead of an actual needle. And what it does is this chassis moves outward and will position the pickup head, which has the laser in it, where it needs to be to read the information off the disk. Okay? That's what's going on. So we obviously want to minimize any vibrations that happen here, right? We talked about this. So we start our system just like we start every other system. Our free body diagram, right? In this case, we need 2. In this case, we need 2. Right. So I'm assuming that x in is greater than x2 is greater than x1, right? And x in is just my input here. Hopefully everybody's cool with the free body diagram, but if not, let me know. We can talk about it. We've got our free body diagrams. Next thing, right, we determine our inputs and our outputs. Well, for this particular case, our input is shockingly going to be x in, and our output is actually going to be x1. So we are interested in what? Yeah. We're very much interested in determining how much vibration is being passed along to the pickup head, to where the laser is. So x1 is going to be our output of interest. I mean, x2 could also be, right, if we wanted to know where the chassis was, but we don't. We want to know where the pickup head is. Right? Truths. Sum of the forces for block 1 is equal to mass 1 x double dot 1. FB1 is equal to B1 x dot 2 minus x dot 1. FK1 is equal to K1 x2 minus x1. Sum of the forces for block 2. All right. And these should be 2. Right. So I'm going to go back to the free body diagram because I did it, but I didn't talk about why I did it. Right. We'll be back in a second. Okay. I assumed all of these things I assumed everything to be in compression. Right. Why did I assume everything to be in compression? Because why not? There's really no reason. You can assume them to be whatever you want. But you have to draw your forces the right way, right? So if I assume that x in is greater than x2, this is going to compress. If that's compressing, the spring is pushing back on everything, right? Same deal with mass 2 and mass 1. If that space is compressing, the springs are forcing back out towards the masses, right? Listen. Good question. So the question was, in case you guys didn't hear at home, do you need to assume that both sets of springs and dampers behave in the same direction, right? And the answer is no. You can choose whatever you want, as long as when you draw your forces, you're consistent. Because then the math will play out, right? Because instead of having, so if I flipped it, right, say I said that, K1 and B1 were in tension. If I had flipped that, I would get x1 minus x2, and then the sign in front would also change, which would bring it back to what I originally had written for compression, right? So the signs will take care of themselves as long as you're consistent and you've drawn the force the correct way. Good question. All right, so here we are. We got our truths. And both of these are free end, which is everybody's favorite kind of spring and damper, right? When you have to make sure that you carry the free end around, because that's a fun thing for bookkeeping purposes. Dr. D, you're weird, and I don't understand what you think is fun. And you know what? You guys, that's the great thing. You guys don't have to worry about that. Okay? All right. Here's where we get into the fun part. The reduction. Now, question about this system. What order system is this? Oh, I heard it. Fourth. Right? Trevor is correct. It is a fourth order system because there's two masses, and both of those have some of the forces equal to mx double dot, right? So we've got two second order equations. So overall, everything here is a fourth order system, right? But that doesn't matter just yet, but it's good to remember, keep in the back of our head. So I'm going to start with block 1. Why am I going to start with block 1? Because it's called block 1. I don't really have a good reason for you. There's no reason why you can't start with block 2 if you want to. That's fine. Okay. But let me ask you this question. If they didn't want you to start at block 1, why did the textbook call it block 1? Okay. M1x double dot 1 is equal to the sum of my forces, which is just FK1 plus FB1. This is the real reason why I wanted to start with block 1. It's a little bit easier, right? There's fewer terms. I don't have to deal with as much. Right. K1, FK1 is just K1 x2 minus x1. Right. So we have this. I can algebra a little bit. Right. So just rearranged. I might input output equation, right? Inputs on one side, outputs on the other. And then I know that this eventually is going to, so they want me to make the model, right? And so there's a couple ways that we can talk about making the model, right? But the thing that we've been talking about most right now is the transfer function, right? Because we're doing frequency response. And eventually we're gonna have to do something with the Bodie diagram, right? And even if we're gonna use MATLAB to get the Bodie diagram out, we need a transfer function, right? So we're gonna take this all the way to the transfer function. Which transfer function, right? Because there's technically two outputs, but we defined x in as our input and x1 as our output. So we want to get the ratio of x1 to x in. That's what we want to get. Okay, so if we're going to go for the Laplace transform, or if we're going to go for the transfer function, we'll take the Laplace transform with 0 initial conditions. That's going to give me m1s squared plus b1s plus k1 times x1 of s is equal to b1s plus k1 x2 of s. Right? And because, and this is fine, and we could leave it here if you want, right? But we know that we're going to want to eliminate that x2 at some point, right? Because we want everything in terms of x1 and x in. That's what we want to do. So I'm going to solve this for x2 right now. All right, I'm going to come up with an expression for x2 of s. And x2 of s is equal to m1s squared plus b1s plus k1 over b1s plus k1 times x1 of s. All right, everybody with me so far? Any questions as to why we're doing this, right? So why Dr. D? I feel like I need to explain this, and I didn't explain it well. Why, Dr. D, do we solve this for x2 of s? Well, there's a couple of reasons. First of all, we know that we still have to reduce half of it, and x2 is going to show up there. And we want everything in terms of x1 and x in. So we're probably going to have to substitute this in. Right, so a little bit of foreknowledge about what our other truths look like, and understanding that in order to get x1 into the next part of the equation, I just broke my chair. Okay, the foot thing off. I don't know what to do anymore. All right. So in order to get x1 into the next part of the equation, we need to eliminate x2, and we do that by finding an expression for x2 in terms of x. Now we're going to do block 2, right? M2 x double dot 2 is equal to fk2 plus f b2 minus fk1 minus f b1. Right? So the question came up last class. What if we started with block 2 and then we substituted into block 1? Well, you'd get the same answer, right? You'd get the same answer. All right, so FK2 plus FB2, right? We can substitute in our values here. Okay. So we're going to algebra now, right? So we're going to get all of our x2 and x1 terms on the left, and all of our xn terms are going to stay on the right. And if we do that, we'll get this big expression, m2 x double dot 2 plus b2 plus b1 x dot 2 plus k2 plus k1 x2 minus b1 x dot 1 minus k1 x1 is equal to b2 x dot n plus k2 x n. That's a 2. Let's write k2 better so people can actually read it. There. Whew. Okay. Now we take the Laplace transform of that with 0 initial conditions. Sorry, that's not x2 on the back end. That's xn. My mistake. Okay, so we get m2 x squared plus b2 plus b1s plus k2 plus k1, that whole thing times x2 of s, right? Minus b1s plus k1 times x1 of s is equal to b2s plus k2 times xn of s. All right. So, all right, everybody good so far? We have any questions? Everybody's doing okay? Okay. So what do we do now? Yep. We're going to substitute in the x2 equation that we came up with on the previous slide. So, because I know you guys love the algebra so much, right? This whole thing times, well, x2 was m1s squared plus b1s plus k1 divided by b1s plus k1. And this is minus b1s plus k1 times x of s is equal to b2s plus k2 times x in of s. Okay, and that's great. But there's one more thing that I'm going to do here to kind of help us out. Right? This is subtracting. And I'm going to multiply this term, b1s plus k1 times b1s plus k1 over b1s plus k1, right? To give it the common denominator. So we get that. And that is lovely. But wait, there's more. Right? Because normally I'll tell you guys, yeah, then just leave that like that, divide it, get your transfer function and you're good. But that's not going to be enough for this because of what we're asked to do. Right? So if you were asked just to get the model, sure. But we need to do some evaluation once we have the model. And so we want it in a specific form that's a little bit nicer for us to play around with. Okay. Everybody good so far?
Just to clarify, that's X1 of that, right?
Yes, sorry. Thank you, Jesse. That's a 1. That doesn't look like a 1 anyway, now that I put it there, but that's what it is. It was there the whole time, from a couple seconds ago till now. I'll edit the video. It'll be fine. It'll be there the whole time. I won't though. It's going to go up right after class. Okay. So what now? Now is the fun part. Again, because we love the algebra so much, what are we going to do? I'm actually going to multiply this entire thing out. And I'm going to get the actual characteristic equation for this system. So we're going to have to multiply this completely. Now you might be thinking, Dr. D, right, on an exam, Dr. D, you're probably going to give us parameters right at the beginning for M, B, and K that we need. And that's true, because if I don't give them to you at the beginning, I'll forget completely, and the problem will become impossible, and then I'll have to make them up on the fly during the exam, and I'll forget what I said they were, and it'd be a massive cluster. So we're just not going to do that. But, so Dr. D, why? Why not just plug these numbers in now? It'll make it look so much nicer, and you won't have to deal with all this algebra. That's certainly a thing you could think. And it's certainly a thing that could work. But it is also a thing that makes your model completely one-dimensional. If you plug in the numbers to start with, and then one of those numbers changes, you have to do everything again all the way from the beginning. Whereas if you do it symbolically all the way to the end, then all you have to do is calculate a few things right at the end. Or if you're doing it in MATLAB, change your M, B, or K, whatever happens to change, and rerun it and get out your answer again, right? But I digress. Let's get on with the algebra. So we're going to multiply this whole thing out. So what do we get? Whoa, it's haunted. M1 times M2 S to the 4 plus M2 B1S cubed. All right, so what am I doing? I'm literally going piecewise and multiplying each of these things out and distributing it as we go. Square. There it is. That is the thing. In all of its glory. And if you gaze upon it for too long, your hair will turn white, right? You don't have hair, right? You'll grow hair, then it will turn white, like Zoidberg in Futurama. Right. Also, if you're not watching or you haven't watched Futurama, you've got 2 weeks between semesters. I highly recommend you watch Futurama. More than you can watch in 2 weeks. Challenge accepted. Okay. So that's where we end up with, right? So instead of us going through and rearranging this whole thing and grouping like terms, what we're going to do instead is we're going to look at each of our s to the fourth all the way down to s to the 0 terms, and I'm going to create constants to represent them. And then we'll calculate those constants later. Right? So starting with s to the fourth, right, we're going to group our constants here. Well, I only have one s to the fourth term, right? That's m1 times m2. I'm going to call that a. Why am I going to call that a? Well, it's the first one. It makes sense. You call it whatever you like. Call it whatever you like. If you are going to put this in MATLAB, you'll notice that I am doing this as capital letters on purpose, because if you try to use lowercase e in most programs, it will break. You'll break. Right. So stay with certain variables. Stay away from. Right. Just heads up. S cubed. That's m2 b1 plus m1 times b1 plus b2, which I'm going to call capital B. I'm doing way better with this. I could not, for the life of me, write the correct variable letter last class, and I tried to call a lot of these C, like more than one of them C. Because really, I don't know what's going on. But apparently, alphabet is hard. So, all right. So again, what are we doing, right? We're doing the same thing that we would do algebraically and grouping our like terms, but because all of these are constants, as much fun as it would be to write m2 b1 plus m1 times b1 plus b2 for the next few things that we're going to do, I'd rather not. I'd just rather not. So s squared gives us m2 k1 plus b1 squared plus b1 b2 plus m1 k1 plus k2 minus b1 squared. And that's nice because these two go away. Right? We've got b1 squared and minus b1 squared, so those will cancel, and that will leave us with m2 k1 plus m1 k1 plus k2 plus b1 times b2, and I will call that C. My s to the 1 terms, k1 b1 plus k1 b2 plus k1 b1 plus k2 b1 minus twice k1 b1. Well, these two would add up to 2k1 b1. Then I can subtract 2k1 b1. So this is b1k2 plus b2k1. That's equal to d. And so just so we can kind of see what our equations are. And we've got one more, s to the 0, which is k1 squared plus K1, K2 minus K1 squared. And these cancel, and we're left with K1 times K2, which I'm going to call E. And this has the added benefit of what we're about to write down. In a second, I'll give everybody a little bit to write. Any questions so far? Any questions? Comments? Concerns? Okay. Give you guys another second. All right. So if we do all of that, we can simplify it down to this. Right, and we can calculate A, B, C, D, and E if we get parameters later. Right, we can do that. So the next thing that we need to do, right, is turn this into a transfer function, right? And we can do that, right, because g of s is equal to x1 of s or xn of s, which is b2 s plus k2 times b1s plus k1 divided by as to the fourth plus bs cubed plus cs squared plus ds plus e. Right? So I'm going to multiply the numerator out now. And I'm going to do the same thing here that I did before, where I take this and I assign a new variable. I'll take this and I'll assign a new variable, and I'll take this and I'll assign a new variable. So
the variables that you used before to simplify the same?
Yes, you can. We'll talk about that in a second. And just just for completeness, right? That equals E, and G actually equals D, right? Okay. Everybody following? Do you have any questions about how we got here? I'm sure there's questions about why. Why you do this, Dr. D? Why you do this to us? Because it's Christmas and my heart is 3 times smaller than normal. Right? Also, by the way, if the Grinch's heart actually did grow 3 times its size in that amount of time, that would be very bad anatomically, just in case you were wondering. I've written a letter to the estate of Dr. Seuss about it. I haven't heard back yet, so. It was a problem to begin with.
I think that's assuming he has a human heart.
Yeah, I guess I am assuming that the properties of the Grinch's heart would be, human. I thought he was just like a green-haired human. I thought he just dyed his hair. Like he was just like a really hairy dude. Anyway. Sean, I spent 5 years in graduate school researching this topic. Okay, and gotten nowhere. Anyway, now that we've wasted that time, we'll never get it back. What is the DC gain of this system? What is the DC gain for this? F. No. What is the DC gain in general? What is it? What is synonymous with DC gain? K. Okay, sure. And what is K? You say the DC gain. This is going to happen over and over again. No, we got to get out of this loop. H over E, 100%. Nailed it, Olivia. Why, though? Why? How do we find the DC gain? Yeah, you plug the zeros in for S, right? Because why? Because DC gain is synonymous with the steady state gain. And what is special about steady state is we are not changing as a function of time. And if we're not changing as a function of time, all of our time derivatives are equal to 0. And in the Laplace domain, S is the time domain. Or in the Laplace domain, S is the time derivative, right? So it's equal to H over E, which is just 1. Correct. And if you converted this to decibels, what would it be? You can use your calculator for that. That's fine. I can't do log math in my head. It's 0. It is 0. So the other class asks, if it's all 0, then why? What was the whole point of doing this? It's not always 0. This just happened to be 0. 0 decibel magnitude is important to understand what that means. That means that we are not attenuating, but we are also not amplifying, right? Whatever you put in is what you will get out. Why? Because it is the same as scaling my steady state response by 1, right? So remember, when we're asked about steady state response, right, the equation is YSS is equal to magnitude of G of J omega times the original amplitude times the sine of omega t plus phi, right? That is the equation. Right? If this is equal to 1, then we get U naught back out. Right? On the Bode phase and magnitude plots, right? On the magnitude plot, we write everything in decibels. 0 dB is where we have equivalence, right? We're scaling by a factor of 1. Okay. 0, naught. Okay. Man, oh man. We are just cruising. Right, so we got the model. Where do we say we stop to get the model when we get G of S? Getting G of S means that we did enough to say we got the model in this case. Why is it for this case? Well, I told you guys before. Because we are going to need to create a Bode diagram, not by hand in this case, because we haven't talked anything about drawing asymptotes for anything higher than a second order system, right? So for something like this, you would need to either be provided the Bode diagram, or you would need to be able to use MATLAB to get it. One or the other. Okay. But because we need the Bode diagram and we're going to use MATLAB, we need the transfer function or state space. So you guys could have done state space for this if you wanted. Seems like an awful idea that you could have done. Here's some parameters. I took apart my Blu-ray player and I tested these this weekend, but not really because the book just had some, so I'm just using this from the book. I did not. I took their word for it on this one. And you know what, Jesse, that's just a good point. We'll have to get a capstone project on that for next year. Okay, so here's our parameters, right? We've got our mass, our stiffness, and our damping for both the pickup head and the chassis. And so what we're going to do is we're going to go back and we're going to calculate A, B, C, D, E, F, G, and H. That's what we're going to do. So I'm going to give you guys a second to copy these down for your notes and whatnot. And I'm going to write down these on the next slide. So I'm not going to go through the arithmetic to get these, right? I'm just going to write down what I calculated when I plugged them in. So everybody's got them, hopefully. Oh, that was weird. Glitched out for a second, but we made it. All right. At A, B, C, D. All right. Well, D is equal to G. E is equal to H. And F. So these are the values we get. And yeah, we're going to plug these into our transfer function. Let's do that. So G of S is equal to 0.1869 S squared plus 432.6 times S plus 11,600 divided by 7.44 times 10 to the minus 5 S to the fourth plus 0.007476 S cubed. Okay. So that's good, right? That looks fantastic. Looks very good. Looks better than it did before when it was all the M's, the B's, and the K's. Right? But there's still one more thing that I want to do. I'm going to kind of put this into sort of pseudo standard form. And I'm going to divide through by 7.44 times 10 to the minus 5. Okay? So I'm going to clear that S to the fourth variable. Why am I going to do that? Well, you'll see in a second. All right, so if I do that, okay. So this is our transfer function, right? This is our transfer function. There's our transfer function. It's a little sharper. These are transfer functions, the same one that we had on the last page, right? But why did he do this? Part B of the problem, right? Asks us to determine the operating frequencies, right? Determine the operating frequencies for what? For an impulse response, right? I'm gonna smack this with an impulse, and something's gonna happen, and I want to know what my operating frequencies are. But Dr. D, that's not a sine wave input. And frequency response only applies to sine wave inputs. I don't know how we're gonna get the frequency. Good point, right? Good point. So this is how we're gonna get it. Well, first, I want to talk about an impulse. An impulse, right? An impulse, let's say the unit impulse, is 1 times delta of t. And if I take the Laplace transform of this, it just returns 1, right? Actually, if we talk about this in the general sense, where I have a times delta of t, this will always return a, right? And if I was to analyze this transfer function using the transfer function method, I would need to multiply by the Laplace transform of x in of s, right? And multiplying by the transform of x in of s, which is an impulse, would just be multiplying by a constant a, right? And multiplying by that constant is just scaling the response. It's not doing anything else. It's not adding any, it's not a over s, right? It's not adding another root to the system. It's just a scaling of our response. That's all that it is. So what is our response, right? What is our response? How are we supposed to figure that out? Well, it's going to be the natural dynamics here, right? Which means that we need to find the roots. So I need to find the roots of this 4th order system, right? And the easiest way to do that is to put it into your favorite solver, set it equal to 0, and solve for s. Okay, that's the easiest way to do it. You could also do polynomial long division and create 2 second order systems, right? You could do that, but we're not going to do that. I'm just going to use my tools, right? I'm going to use my tools. I'm going to say that by solving this, S1 and S2 were equal to negative 25 plus or minus 123. I don't know why I keep putting a hat on that. It's just J. And S3 and 4 were equal to minus 25 plus or minus 316 J. What kind, so we got 2 sets of complex conjugate roots out, right? 2 sets of complex conjugate roots. What sort of system response are we expecting? Stable, sure, but describe the shape of the curve that we're going to get out of it. If you have complex conjugate roots, there's a specific response that we can expect, right? Think back to when we talked about root responses at the beginning of time domain. Yes, Olivia, underdamped decay is correct, right? You will get a damped oscillation, right? Well, it's an impulse. So think about what that means, right? For an impulse, that means if after I hit it, I'm going to reach a level, and I'm going to come back down to 0, oscillate about 0 until I steady out, right? That's what it's going to look like. So let's talk about what this means on the real and imaginary axis, right? So we can draw this, right? I know that I've got negative 25, so along the real axis, I'll say, you know what, this, sure. this is negative 25 right here. Okay. And I'll say this is 123. Right. So I'm going to have half of my complex conjugate here, and the other half will be at negative 123j, but at minus 25, right? So it's just going to be mirrored on the other side of this axis. So I'm not going to draw. There's my other one. So there are my two roots, right? Remember, there's a complex conjugate on the other side of the real axis. That's great. All right, so what does the real portion of this root indicate to us? What does the real portion mean? If I had a purely real root, what kind of response would I expect to get? What does the real portion tell me? Was that? What's that? The real portion gives you information about the exponential, right? So what does the imaginary portion tell me? If I had a purely imaginary root, what would it look like? No real portion, just imaginary. Not straight line. Where is this? Marginally stable, which looks like, yep, harmonic oscillation, right? So the imaginary axis must have something to do with this oscillation, right? And the real axis controls this exponential function, right? That's so what ends up happening, right? Remember, I'm trying to find this really quick because we talked about it in an old lecture. So I want to try to pull up the plot that I'm thinking of. I think it's here. Yeah, I'm not gonna find it. Oh well. Find it for next class. So as we increase omega, right, as we increase this on the imaginary axis, what happens? We increase our frequency. Turns out that 123 is our omega, and 316 is also our omega. We have two frequencies here. These are the operating frequencies for an impulse. Okay. Remember, the roots take this form. S is equal to sigma plus j omega. The real portion controls the exponential, right? So looking at this, I should have e to the minus 25t. You know, I'm not going to put the sine or cosine in there, right? But it's, well, I'll just do it. A sine 123 t plus b cosine 123 t, right? So I don't know what a and b are, and there's probably some coefficient involved. So I'm going to have to come up with all that, right? Okay. That's fine, because we're asked for the operating frequency, and we found that. It's 123 radians per second and 316 radians per second. And all we have to do for the low price of finding the roots, which is something we were going to do anyway, likely, because Dr. D is always saying, did you check the roots? Did you check the roots? Well, you should probably check the roots. Check the roots. But if we check the roots, we automatically get our standard operating frequencies, right, in this case. Now, here's another question. What is the time constant for this system? The time constant. He's always asking us about the time constant. Why is he always asking us about it? 1 over tau. So it's tau, it's not 1 over tau, it is tau. Right? It's 1 over something. It's the amount of time that it takes us to form e to the minus 1, right? So what is it? Well, if I take the natural log of both sides, what's tau? So if you have the roots, right? If you have the roots, you have information about the time constant. If you have the roots, you have information about the frequency, right? What happens if this wasn't so nice and this wasn't negative 25 and negative 25? What if it was negative 25 and negative 100? Well, you have 2 time constants. We talked about how to handle that one, right? We call the dominant time constant the slower one. Why? Because it's going to stick around longer. Why? Because what's the settling time? 4 tau, 0.16 seconds. And if you had another thing that was at negative 100, you'd have negative 1 over 100, which would be 0.04, right? As a settling time, which would be faster, which means that the transients would go away sooner, which means that this is going to dominate our response. Okay. What about the Bode diagram, right? That's the last part we need to talk about was the Bode diagram. Well, if you go in and you do the Bode diagram in MATLAB, you should get something that looks like this. We've got 2 peaks. All right, so we didn't talk about it, but why do we have 2 operating frequencies? Well, you've got 2 masses. And if you apply a vibration at the front end, right before, in this case, if I smack it, the middle one's going to vibrate at 1 speed, and the final one's going to vibrate at another. So the middle one will probably vibrate more, and we'll get more damped out by the time we get to the pickup edge, right? So we have 2 vibrational frequencies because we have 2 masses that are both vibrating at different frequencies. Right? And that's due to the natural dynamics. And those both have peaks here and here. So if you wanted to, right, you could maybe draw the asymptotes for this using the rules that we have. Right, so what would we do? Well, we've got a second order system, so we would come over, we'd have a 0 dB gain until we get to our first corner frequency, which would be the natural frequency for that first mass. And then we'd have our high frequency asymptotes start to go down by 40 dB per decade. Then we hit the next one and we drop by another 40 dB per decade, right? And we just cause this sharper asymptote. But we don't have to draw these by hand, right? Because these are higher order systems, and I told you that you wouldn't have to do asymptotes or anything over second order. So what can we pull off this magnitude plot? Right, there's some interesting stuff. First of all, let me ask you this question. At what frequency will I begin to attenuate all vibration? Approximately. Which one? No, that's the beta, right? That's √2 is the frequency ratio, right? So that's when omega over omega n is equal to √2, which we don't have an omega, right? We're just trying to. So if you had to pick this, so if I asked you to tell me the range of frequencies or the frequency where we would start to attenuate, what would you pick? That's bandwidth, right? And we'll talk about bandwidth in a second, for sure. Remember, attenuation is when we start to degrade our signal, right? Attenuation is, in this case, attenuation is when we start to lessen the amplitude of our vibration. It's not the 0.707.
Is that the W per omega R2?
It's close to omega R2. Olivia, yeah, there's one point in there where you would drop below 0, right? But for long term, right? So when you're asked when it's going to start to attenuate, what it means is when we drop below 0 dB, right? Because when we drop below 0 dB, we're losing magnitude, right? That's why the dB scale is nice, because at 0, you're not adding or subtracting anything to the system. Above, you're going to add something, and below, you're taking something away, right? That's why it's nice. But in this case, right, around here, around right there, right? And so if you had to read that frequency off, what would we say? Well, we'd say that that's 100, 200, 300. That's like 325 radians per second-ish, yeah. Remember, the 10 to the 2, it starts at 100. The next tick mark is 200, then 300, right? I disagree, Trevor. I think that using non-logarithmic is weird. And I think using non-logarithmic is weird. And this is nicer and cleaner. And I think that they should put football fields like this. Oh. Yeah, exactly. You pick up those first downs much quicker as you progress. All right. Okay, so that's a question that could be asked, right? Tell me what if it was like, when do we attenuate by a certain amount, right? Well, if you're giving it in decibels, you just go over and you read it. If it's, attenuate by 50%, we did that problem in class last time, right? You find G of J omega is equal to 0.5. You translate that into dB, which is -6.02, right? You find that on the plot where the frequency is, all right? What's something else we can ask? Bandwidth, right? Let's talk about bandwidth. When we start at 0, if I -3 from here, there's no way you're going to be able to see it because the next thing's at 50. And there's no way I can draw that accurately, but we're going to try it anyway. It's going to be like right here. All right, so this is like -3 dB, right? So you subtract 3 dB from your DC gain, draw a line. Where does this cross with my Bode magnitude? Right here. Read this off. 100, 200, 300. It's call that like 375-ish, right? Call it like 375. So my bandwidth is this region here, right? So you would say, because it's on the plot, right, like that. Okay, so that's bandwidth. Let's talk about transmissibility. Let's talk about transmissibility. So transmissibility. All right. If I wanted to discuss transmissibility, there's a couple ways we can do it. We can say, find the range of frequencies for which I start to attenuate, right? Which we already did. Or more than likely, what we will see is something like this. You will typically, you might be given transmissibility limits, right? So for certain systems, you might know that, you know what, this is fine as long as I don't exceed a certain amount of transmissibility, right? You know, as long as I don't exceed like 1.5 times what my original input is, I should be okay. In this case, it's gonna be really, I'm gonna do this a little bit backwards. We'll say 1.5 times. 1.5 times is fine, right? So TR is equal to 1.5, right? So you're told that you absolutely, under no circumstances, can you operate this device with a TR of greater than 1.5, right? So looking at this Bodhi diagram, I have to figure out where TR of 1.5 is, right? Which means I've got to take 20 times log of 1.5, which is 3.5-ish, 3.5218 something. So 3.5. So I need to find a dB of 3.5, which I'm gonna say is like here. And I'm gonna come over, and similar to bandwidth, I'm gonna find where this hits, right? Well, now anything above this is no-go, right? I should not operate in this range. If I operate in this range, I will violate my transmissibility limits and something bad will happen. Similarly, it keeps going, right? And let's say it hits the peak. We don't operate at 311 radians per second either. So we can operate between here and here. We can operate between here, and then from here all the way forward, right? So we can set transmissibility limits, and we can figure that out as well, right? So if you're told it might be not told you as transmissibility, but we can't exceed 2 times the input, right? Well, log of 2 should be like 6.02 because log of 1/2 is negative 6.02. Right, so you just find every frequency that has a magnitude above that point, and you say, no thank you. Also, another response to that question would be, no, we can't have a transmissible, we have to do something because our operating frequency is right in that gap right there, and we have to run it there because that is the operating frequency. Last thing we'll talk about with Bodhi plot. Can we, all right, what's the resonant frequency? What's the resonant frequency? What's the most resonant frequency? So remember, resonant frequency is the frequency at which we have the maximum magnitude response. So which one of these two frequencies is the resonant frequency? 123. Right? Why don't we want to operate things at resonant frequency? Great question. Because if you're a mechanical engineer or a biomedical engineer, shaking things near the resonant frequency is bad. Remember the transmissibility plot that I showed earlier? The closer you are to beta is equal to 1, which is omega equal to omega n. The closer you are to resonance, you will get large spikes depending on how much damping ratio you have. The lower your damping ratio, the larger the spike. So what happens when you get into Cohen-Arrow bridge situation, right? Because you get a near infinite amount of transmissibility. So you're just slamming this thing with excess vibrations. Right? What about the space block? What can we get off of this space block? Honestly, don't. Okay? The phase plot's all about the timing of the system, and for this class, we're talking about systems under their natural dynamics, right? We're not talking about applying control systems or anything. In general, we talk about lead and lag, right? And lag is what we see here, right? You're lagging behind the signal. I think this makes physical sense to everybody, right? If I push on a block, there's going to be some delay between when I apply the force and when the block moves, right? You can also get into situations where you have lead, and lead means that you get the output before you apply the input. I know, but that's an artificially created thing, right? That's not something that typically happens in nature. When you see that is when you start applying control systems and these types of control systems called lead lag compensators, which we're not going to talk about. This isn't a side right now. But that's where this kind of heads. Okay, but just because you don't have to draw this, right, doesn't mean you can't get something useful off of this plot, right? If you were given this Bode diagram, could you produce the steady state response at a given input? What if I told you I want the steady state response for this at 1,000 radians per second? Or let's give you a sine wave. 5 sine 1,000 or t. What does that look like? We did one like this in class, right?
Standard form is normally written in degrees or in
Radians. Phi is always written in radians when we do it in calculation, but it's always given in degrees in the Bode plot, which makes it very convenient. You will have to do a conversion, right? All right, so we want the frequency response. We want Y steady state at 1,000 radians per second. So what do? Well, first, let's identify 1,000 radians per second. This line right here. Right? There it is. Okay. There's the magnitude at this point, at this frequency. Come on over. Yeah, negative. I don't know. 40? Maybe 40? It's hard to tell on this one. Make your best guess, right? Just don't tell me that it's like 0. It's clearly not 25. Like 30 to 40, somewhere in there, right? We'll go with 40. So G of J omega in decibels is equal to negative 40 dB. I need to convert this to unitless, right? That means I need 10 to the negative 40 over 20. Where does that come from? Good question. Where does that come from indeed? Remember the original equation, we talked about this at the beginning of class, I think. If we didn't, then that's fine. Right? Right? But I want to solve for g of j omega, not in decibels, so I have to take everything. I have to divide by 20 and take everything, put everything to the 10th power. And that's where it comes from. I'll just solve that equation. So that's what we get. If we plug that in to our calculators and solve it, what do we get? Somebody let me know. .01, nice, nailed it. All right, so this is equal to 0.01. So g of j omega, oh, no, thank you, equal to 0.01. What about my phase? Yeah, you know, negative 260-ish, sure. Got to convert that from degrees to radians, right? So multiply 260 times pi over 180. I said we're going to solve this with 5 sine of 1000 t. So y steady state is equal to 0.01 times 5 times sine of 1000 t minus 4.54. And you got the steady state response. So it doesn't matter how crazy your Bode diagram looks. If you know what the input is, you can always find your steady state response, regardless of any order, right? Okay. You guys have any questions? Nope. Maybe not. Being able to read the Bode diagram is really helpful, right? Because we can get a lot of information off of this. Get a lot of information off of this. Okay. In order to get some of this information from the Bode diagram, right, we need to know either a starting magnitude to get a frequency or a frequency to get a magnitude and a phase. Right? You need to know something. I can't just give you the Bode diagram and be like, tell me all the things about the Bode diagram, right? Because it's very dependent upon the context of what you're being asked. We don't have 60 minutes, and the other class also didn't have 60 minutes. So we're not going to do this as a time trial, but we're just going to walk through this problem. So what I'm going to do is I will put, so I think this is a good problem, and I think you guys should try it on your own later. So what I'm going to do is I'm going to look at YouTube, and this is 1 hour and 54 minutes in. So I will put a timestamp in the video so you can get back here, right? So what do we need to do, right? We're going to run this tip to tail. We'll do it together. We want to find the model. In this case, since we're being asked about frequency response stuff, that's going to mean find the transfer function. We want to determine the steady state response for a specific input force, 2 sine 8t. We want the Bode plot, so we're going to use MATLAB to get it, right? Because why? Because we need to find the bandwidth. And trying to find the bandwidth from your asymptote plot is not going to turn out well. right? It's not. Finally, you want to determine the frequency where the steady state amplitude is maximum. And there are some parameters, right? M is equal to 0.6 kilograms. B1 is 3 newtons second per meter. K is 80 newtons per meter, excuse me. And B2 is 0.4 newtons second per meter. The other thing you want to notice here is that the bases, right, both bases are fixed, right? This is hanging between two fixed platforms, and the mass itself can oscillate, but the bases will not, right? So these are both fixed springs on both sides, fixed on both sides. So the first thing that we have to do, right, first thing we have to do is always is our free body diagram. Right, so here it is. Here's our free body diagram, looking good. We have some input force. We've got FB1, FK, and FB2. Our input is FA. Our output is X. Our truths, some of the forces MX double dot. FB1 is equal to B1 X dot. B2 times X dot is FB2. FK is equal to KX. And FA of T is equal to 2 sine 8T. I do my reduction and I put the whole thing together and I take the Laplace transform. Right? I take the Laplace transform with 0 initial conditions, right? Because I'm going for transfer function. Going for the transfer function. In doing so, I'm left with this equation here. Right? MS squared plus B1 plus B2S plus K all times X of S is equal to FA of S, and I can create my transfer function, right? All right. So I'm going to give you guys a second to find the transfer function. I'll give you a couple minutes. You guys want another minute, or you guys feeling good? All right. The transfer function. What is it? Who would like to volunteer their transfer function as tribute to the Hunger Games? Nobody? And the Hunger Games are kind of brutal. It's not really like a great children's book if you really think about what it's about, right? Anyway. But it's presented in a rosy light, so it's fine. Here we go. The transfer function. Right, and if I move my mouse, the people in the classroom will also be able to see the transfer function, and that will be fine. 1 over ms squared plus bs plus k, right? I just added the b's together. Right. There it is, right? Then I plug in my numbers, plug in my values, then I put it in standard form. And this is one of those times, right? This is one of those times where if you put this in standard form, what is your DC gain? Yes, 1.67 over 133.3. That's the DC gain. So it's not 0. It's actually much less than 0, right? Okay, so we go through, we find J8, right? G of J8. Want the magnitude here? No, I didn't. Let me rewrite this, right? This is going to become 133.33 minus omega squared plus 5.67 j omega, right? And so that's 132.33 minus 64 because 8 squared is 64. And so if you do the Pythagorean theorem of my real and imaginary for both the numerator and the denominator, right, we'll end up with 0.02 as our magnitude at 8 radians per second. We also need phi, right? So we need to take the angle of the numerator and subtract the angle from the denominator. In doing so, we get minus 0.579 radians, right? Again, it's the tan inverse of the imaginary portion divided by the real portion in the numerator. I know it says 0 over 1, but it really doesn't matter what the real portion is if there is no imaginary portion. right? It really doesn't matter. And there we have it, right? Plug into our, remember, said this, if I've said this once, I've said it 100 times, but the general form of the equation, which is also on the master sheet, but Dr. D keeps repeating it, so it must be important, is this. There it is. You guys really wanted to have a lot of fun. You could take your models for the rotational mechanical system from that lab that you made and run the Bodhi diagram and see what it looks like. One of them. For next year, it is my goal to get an encoder on there so I can just give you the speed input. And then when you run that, then you run the model with the speed input. That's my goal. That goal didn't happen this year, thanks to COVID. Next year, we'll make it happen. All right. So now what? Now we need the Bodhi diagram, right? So we go to MATLAB, we take this transfer function, right? We say, hey, excuse me, MATLAB, if you're not too busy, I would really appreciate it if you could turn this into a Bodhi diagram for me. And then you do that and you get this. All right, hey, that looks like a second order Bodhi diagram. It is, right? Good. Good thing too, since we started with a second order model. All right, we could draw the asymptotes for this, right? We know what we're supposed to get. Right? The DC gain of a really small number, right? But hey, take a look. What's happening here, right? We got minus 40, right? Roughly minus 38. We come up, we have a spike, which is at the corner frequency, which is going to be what? Well, that's going to be omega n for us. So,
We have MATLAB on the test.
nope. So what? So this is what I do by hand. I do the asymptotes, and I fake what it would look like. Because I'm not going to grab anything of meaning from this, right? I'm not. It's just like to do bandwidth, you need to be given a Bodhi diagram that you can actually look at and estimate from, right? But what I can do by hand is draw the asymptotes, right? We can take a look at this because I'm going to go back to the Bodhi diagram itself, right? So what did we do? Well, I said omega n is 11.54 radians per second, right? Why did I say that? Well, because 13.33, the square root of that is 11.54. I can also find zeta, but we'll talk about that in a second. Before we get there, let's go back to this Bodhi diagram, the actual Bodhi diagram. Okay, so we know that at what? It was 11.554, right? That's our corner frequency, 11.54. Tools, data tips, is already on. Right, so if you use tools data tips, you can use your arrows, left and right arrows to move along, right? So we were asked for the bandwidth, okay? We start at minus 38 decibels. How do we find bandwidth? We subtract 3 from the DC gain, which is the low frequency asymptote, which in this case would put us down at minus 41, right? And we track along until we find where that crosses, and it's right there. So our bandwidth is from 10 to the 0 until, so from 1 radian per second to 17.2 radians per second. 17.2 radians per second is what we consider to be our cutoff frequency, right? Which is obviously given the letter omega p. The omega c is taken. It's the corner frequency. So if you have the Bodhi plot and you have it in MATLAB, it's very easy to get. It's really easy to get the bandwidth, right? What if you didn't have MATLAB and you just give it a Bodhi plot, right? Somebody walks in, throws this Bodhi plot on the desk, says, tell me the bandwidth. You can estimate it. You can look at it and say, oh, that looks kind of like where 3 dB less would be, right? And you get in the ballpark, and you could say, you know, it would be somewhere around here, but I would need to double check when I get back to my office, when I have access to a computer. Although you really don't have an excuse anymore because your phones can run MATLAB, so it's fine. I'm really glad that wasn't a thing when I was in grad school, by the way. But anyway. All right. So to tie this up, right? We found the bandwidth, 17.1 radians per second. We need to find the point where the frequency where we have the maximum amplitude, right? That was the question. What is that? What is the frequency? What do we call that? The frequency of maximum amplitude. What do we call that? The resonant frequency. And we have an equation for resonant frequency, right? Resonant frequency tells us that omega r is equal to omega n times the square root of 1 minus twice zeta squared. Well, we know omega n, right? It's up here. We can calculate zeta, right? Why? Because remember, 2 zeta omega n is equal to that second term, right? B over m, right? But we have this in standard form already. So we know that this has to be equal to 5.67 from our equation. And if we rearrange it like we see right here, we find that zeta is 0.246. We plug this in, and we say, well, omega r is 10.82 radians per second. But we also have the Bodhi plot, right? So let's double check it on our Bodhi plot. Come back here. Yeah, 10.8. Right? We're good. Nailed it. Okay. So those are basically the things, right? Those are basically the things. Do you guys have any questions? All right, we do have a little time. So we'll talk a little bit about what rotating unbalance is. The next class, we will talk about how we calculate rotating unbalance. Then we will do our case study, which will be more MATLAB heavy than handcalc heavy. And then we will have you ask some questions, and then you will do your makeup points for exam 2, and then you go home. Then probably have a nice dinner. Then you would study and do all the rest of your work. Then you'd have a day off from seeing me, and then you would take the exam. Roughly. Predicted. Probably some other stuff. You guys don't have any other classes, right? So it's fine. All right. So what is rotating unbalance, right? Well, rotational unbalance is common cause of sinusoidal forcing in a machine. So think of it this way, right? I don't remember if I talked to you guys about this or if this was the other class, or if I'm just repeating myself every day. But Ferris wheel, if you overload one side of a Ferris wheel, what's going to happen? Well, as it comes down, it's going to really come down, right? Because it'll be super heavy on one side and it's lopsided. And when it tries to come up, the motor is going to have to work really hard to push it back up, right? Because it's not balanced. Because you're creating a moment at every single point. And this is going to cause wear and tear on your rotational drive, right? Because it's got to work harder on one side than on the other. This also exists in your washing machine. And your washing machine will turn itself off if it feels that it is unbalanced, right? So if you put a lot of stuff in there, typically this happens with like blankets and towels. Put a blanket in there and it's not sitting dead center and it starts to spin, your washing machine will freak out and turn off. And then when you get home, you get a smelly blanket because it's been sitting in water all day, right? And nobody wants that, right? All right, so it exists to some extent in all rotating machinery because you cannot guarantee that everything will always be perfectly balanced, right? You can't. You can get close for sure, but you can't 100% say that it's perfect, right? And you guys had a whole class on that where Professor Tomford told you, shattered your hopes and dreams about how the second law of thermodynamics just eats everything, reaps everything that you sow, and all those things, right? It's the second law. If you've never taken that class, you would never have known about it, but now you do. And you can't unsee it. All right. It's caused by the fact that the center of mass does not necessarily coincide with the center of rotation. When we talk about eccentricity, right? If we consider the entirety of an unbalanced mass to be lumped at its center of mass, the distance from the center of mass is the eccentricity. Constant omega causes a radial acceleration epsilon omega squared. This causes a force to be exerted on the bearings at the center of rotation, given by F sub r is equal to m sub u epsilon omega squared sine of omega t. Well, that's quite a bit. We'll talk more about it. This is where we stopped with the other class, and we're going to be talking a few minutes anyway. So we'll go back over this at the beginning of the next class. There's only like 2 or 3 slides about it, but you know, it's an important concept for rotating machinery. All right, the final deep thoughts of this message. It's not really that deep. If you could live anywhere on the earth, where would you be? I would be up by the O on the top. Also, this is an exact depiction of what the Earth looks like, because the Earth is in fact flat. I have. It is spectacular. I love, yeah, they did the laser experiment, which was, so if you guys haven't seen it, it's called Beyond the Curve. It's tremendous. Dr. Staggs and I actually did a podcast over the summer about, we did 3 episodes on flat Earth. It was the highest, it was like one of the highest rated YouTube videos that I've ever been part of. It's internet gold. The people that are fantastic. I mean, I can't believe that nobody picked New Jersey. It's really weird. Anyway. There's a lot of stuff. All right, guys. This is the last time I'm going to check in with you on this. Right? If you're feeling on the low end, please got a week before the final exam of the semester. Not, but please come see me. Please come to office hours. Right, all of that. And then that's it. If I don't see you tomorrow, have a great weekend, everybody. Good luck on your capstone presentations if you haven't done them yet. If you have done them, I hope it went as well as you hoped it would.
Once again, sorry I was a few minutes late. I just came from mine.
Okay.
I got a call and help desk folks call. Those call me for classes that start. Anyways, with the blood vessel benchmark,
Yes.
I was trying to do like a one cup for it to confirm like the cell works and whatnot. I was looking at age because reasons. This seems blows Newtonian. Like this equation, I think assumes that it's working with Newtonian fluid. Cell works, it's like blood's not Newtonian. It's not.
Right.
So are they going to be even in the same ballpark then as far as calcs go because of that? I think it's not going to be.
No.
I don't think so. So is there a way for us to compare it with time calcs? Like is there an equation you could put me to for it? If it's non-Newtonian?
Oh, man.
Yeah, see,
It's been a while.
it's been a fat minute. I know. I had a good time.
For Newtonian fluids or non-Newtonian. That's typically a grad level thing.
Okay, good.
Dealing with non-Newtonian fluids. Like ketchup and blood.
All right, mayonnaise.
Yeah.
I didn't want to do like, oh no, let's just throw water in it. Just like that's not going to be.
I mean, if